Hello, welcome to Positive Physics. Today we're looking at capacitor charging. First, for a simple single capacitor with a supply cell, so of voltage V. We've got capacitor of capacitance C in our circuit, and then we'll look at capacitor charging in series and in parallel. So here in our circuit we have our cell, we have our positive and our negative terminals of our cell, and as we know in a circuit, electrical circuit, we have a flow of charge when there's a complete circuit, and what happens with a capacitor is that the plate that is connected to the negative terminal will receive an electron, so a little electron will move around the wires and collect on the plate, so we get a negative charge here. Now inside a capacitor in here is a dielectric. That is the name for the insulator that stops the charge from flowing between the two plates, so there's not a direct pathway of charge. Current will flow in the wires but not actually between the two plates in the capacitor. If that happens, then the dielectric is broken down and your capacitor is no longer working. So we have this little electron that arrives on the negative plate of our capacitor, and we know from GCSE work that where you have a negative charge there is an electric field associated with it. So we have this electric field, which means that an electron on the other side of the plate is repelled away. So we've got this movement of charge and we end up with a positive charge on the opposite plate. So if only one electron moved, we would have one electron here on the negative plate and only one electron would move from the other. So the charge that arrives repels the same charge away. If we had a coulomb of charge arrive on our negative plate, let's add a few more electrons, okay, we would have a coulomb of charge being repelled from our opposite plate, leaving the same magnitude of charge but of the opposite sign. So if we have a charge of minus Q on this plate, we have a charge of plus Q on the other plate. At the end of the charging process, if we were to measure the voltage across our capacitor using a voltmeter, we would find that that voltage was the same as our supply EMF. Okay, so that's a simple capacitor. You've got a charge arriving, repelling a charge from the opposite plate, which means that while the capacitor is charging, there is a current flowing in the circuit, but not, remember, between the plates. The other thing that we need to remember in this situation is that as the capacitor charges, the current that's in the circuit will decrease. It will go down with time. The voltage across the capacitor will increase. But actually, the more charge you add on one plate, the harder it becomes to add more in. So the rate of charging will slow down. And that's actually an exponential relationship, and we'll look at that more later on. So capacitors in series, we've got our supply voltage VT, V total, okay, and if we imagine we've got our flow, that's our negative terminal, positive terminal. Let's look at the first capacitor that we reach in our circuit, and we end up with a negative charge on that capacitor of minus Q. We know that that produces an electric field with a strength to repel the same quantity of electrons on the other side, so we end up with plus Q on the other plate. Well, where did those electrons go? Well, they arrived at the next plate. Make sure I've got the same number. So we have minus Q on the next plate. Well, that means that the same number of electrons have been repelled from the other side of that capacitor. So we end up with plus Q. And I think you can all see where I'm going now. Okay, so those electrons were repelled and arrive at the next plate of the third capacitor, and they repel the same number of electrons from the final plate, which means that we have this current flowing in our main part of our circuit. You would also see that current flowing during the charging process between the capacitors, but remember again, you wouldn't see any charge flowing within the capacitors. There's that gap, that dielectric. So what do we notice? Well, if we come down here, let's have a think about what's going on. We know that in series circuits from Kirchhoff's second law that the total voltage is equal to the sum of the voltages across each component. So if this is our capacitor 1, capacitor 2, capacitor 3. I know it seems wrong to do it from right to left, but because our electrons are flowing that way, I think it's simpler to see at the moment. Our voltage across each capacitor is a share of the total because they're in series, and we notice that our charge on each capacitor is exactly the same. And that leads to a situation, if we look at the equation for capacitance, if we put that up here, C is Q over V, then C1 is Q over V1. All right, and what you find, if we rearrange that, V1 is Q over C1. We find that the voltage across each capacitor is shared in a way that is actually inversely proportional to the size of the capacitor. So if you had your biggest capacitor as C1, it would actually get the smallest share of the potential difference available from the supply EMF. Okay. We can also use this combination in order to prove the equation for capacitors in series, which I'm not going to do at the moment. I want to keep this as simple as I can, but the equation for capacitors in series is 1 over the total capacitance, 1 over the sum of 1 over capacitance of capacitor number 1 plus 1 over the capacitance of capacitor number 2 plus 1 over the capacitance of capacitor number 3. That's tricky to say. And so we've ended up with this inverse situation, which should hopefully remind you as being very similar to the addition of resistors, but not in series, in parallel. All right, and in this, we are applying the total capacitance being the inverse of the total capacitance being the sum of the inverses of the individual capacitances. But the main thing to note here is that the charge is the same on each capacitor, and that's because of how the charging process is linked. So what about in parallel? So in parallel, we've got capacitors in parallel. Same things going on here. We've got our positive and negative terminal of our cell and our VT. Now in parallel, we know that the voltage across each of our capacitors, because there's only one in each branch, will be the same. So that is the same across each branch, and in this case that's each capacitor. We know if we think about the first capacitance on its capacitor on its own, we can think about the electrons arriving at that plate and repelling, because of the electric field, electrons from the opposite plate, and those arrive back at the positive terminal of the cell. So we've ended up with minus Q and plus Q. But if we forgot about this capacitor and just looked at this one, we would find the same thing, that the electrons would be flowing and arriving at this second capacitor and therefore repelling an equal number of electrons from the opposite plate. So we have minus Q and plus Q. And what we find is that actually we've got a charge of Q on this capacitor here, C1. We've got the same charge on this capacitor here, C2. But if we look, we've actually got double the charge stored in our circuit. So Q total, if we write that there, is going to equal the charge that's stored on Q1 and the charge that's stored on Q2. Now, if the capacitance of C1 and C2 is equal, then obviously you would have the same charge stored on capacitor 1 as you would on capacitor 2, so you would just have 2Q. Okay, but if they're different, then the amount of charge that has been transferred onto that capacitor and is stored in this charge imbalance, then you would have to look at the value of the capacitance to find out what that was, because the value of the capacitance is going to control how much charge has been stored. Particularly in this situation, if we go back to the top, because the potential difference across each is identical, because we're in parallel. So here, because the charge is the sum of the charges stored in each branch of the circuit, and our capacitance equation is Q over V. Well, in parallel, V is the same everywhere. So we're always going to have, that's always going to be VT. And QT is going to be the sum of the individual charges. So our capacitance total is going to be equal to Q1 plus Q2 in this instance over V. And what we know is that the charge on capacitor 1, if we look at that individually, so capacitor 1, we know that the charge over the voltage, that's the equation linking them together. So if we rearrange for charge, we end up with C1 VT is equal to Q1. So actually, applying that in to our situation where we know that the total charge, okay, is going to be equal to C1 VT plus C2 VT, and total charge is just the capacitance, the total capacitance times the total voltage, potential difference. Okay, we end up with an equation for CT which equals just simply the sum of the capacitances. So in parallel, we add the capacitance together because the voltage across each, the potential difference across each is identical, and therefore they store different amounts of charge, which is determined by their capacitance. And that, so you will have more charge being stored in this circuit. So we have this total capacitance being equal to the sum of the capacitances. And in series, this time we have the potential difference being shared due to the size of the capacitances, but not in the same way as resistors, remember, it's not in the ratio of the capacitances. And the charge on each is identical because of the way that the circuit works. So the first thing to do is to make sure that you can explain clearly how a capacitor is charged. And then the second thing to do is to make sure that you understand the difference in charging between series and parallel, that the charge is the same on each capacitor in series, that the potential difference is the same on each capacitor in parallel, and then finally that the sum of the capacitances in parallel is simply the sum of all the capacitance, and in series it's the inverse of the total capacitance is equal to the inverse of the sum of the inverse of each of the individual capacitors.